This video presents the development experience and results obtained with the storage project. One of the parts of the project was the development of an electrocardiogram or ECG interpretation system on a field programmable gate array platform. In a nutshell, we developed FPGA-based neural network for multi-class classification of preprocessed ECG. Diagnosis of heart rhythms is solved using a canonical machine learning method of classification using a pre-trained model. However, the technical solution to this problem is made by a non-trivial way of interpreting segmented ECG signals. Segmentation of the ECG signal in the first stage and therefore possible classification by a compact model in the second stage allows achieving the results required for edge AI. We test the solution on the PINC-Z2 board, collecting machine learning inferences with the test dataset. In such a way, we test machine learning algorithms, HLS for ML conversion, Vivada HLS synthesis, and operating the FPGA with the developed bitstream. The heart of the PINC-Z2 board is a Xilinx system on chip that contains an embedded Linux machine with a Cortex-A processor and FPGA on a single die. We configure FPGA as a hardware accelerator that we call from Python code as an overlay function. This function fully implements our machine learning algorithm and works as an external neural network processor for Python code. On a Linux system, Python code is only needed as a convenient interface to this network. Absolutely all machine learning is implemented as a hardware. Here, in the right upper corner, you can see the PINC-Z2 board connected to the Ubuntu host. The screen of the Ubuntu host is the main window of the video. The board PINC-Z2 is connected to the host via Ethernet and setting up a static IP address for this network. The IP address for the PINC-Z2 is 192.168.2.99. So I go to Google Chrome at this address. And see Jupyter Hub running on the PINC-Z2. I have already copied all the necessary files to the PINC-Z2. Everything is ready to test and validate the solution on real hardware. The test dataset in 4,000 examples is a part of dataset that was splitted on training and testing parts. To start the test, I open and run the deployment Python notebook script. Storage, test, deployment. So load script, and then restart kernel and run all cells. The Python code loads the bitstream into the FPGA, which takes our time. After a few seconds, the FPGA is ready and the actual hardware test begins. As a result, a Y hardware NumPy will be created with a collection of inferences. The report tells us about what? About 352 inferences per second, which is a good performance. And what about accuracy? We have to copy the Y hardware NumPy file from our PINC-Z2 board onto our instrumental platform, which is Ubuntu host, and run validation notebook to take the target confusion matrix. Not bad. So, we have a compact and energy efficient solution with high performance and good accuracy. Finally, let me briefly introduce another solution we developed in the project: congestive heart failure or CHF prediction. As in the development of an electrocardiogram interpretation system, here we synthesize machine learning on a field programmable gate array platform and implement it on a low-cost PIN-Z2 board. However, in this case, we will diagnose the heart from the scalar data, not from the time series that represent the ECG. So, I go to Google Chrome on the PIN-Z2 board and open and run the deployment Python notebook script. Loading the bitstream into the FPGA, running. Well, the script is finished. I copied the results file from our PIN-Z2 board to the Linux host and ran the validation Python notebook to get the confusion matrix. Good. Thank you for your attention.